Hello students, welcome back to MKG Online Study and E-Learning platform. Okay, you have written Verilog, you have your module, your code is compiling and you feel like you are done. But let me ask you one very important question. Where is the chip? Because writing Verilog does not mean the chip has been built. There is a complete journey between your HDL code and a real piece of silicon. So in this video, we are going to answer one of the questions. Exactly where does the Verilog fit inside the VLSI design flow? By the end, you should be able to look at the complete flow and immediately point to the Verilog oblique RTL stage. Imagine you just wrote 500 lines of Verilog. Nice, but now what? Does the computer take those lines, print them onto silicon and magically give you a chip? Obviously not. Something happens between Verilog code and real world. This is verification. There is synthesis. There is a gate level representation. There is physical design and eventually fabrication. So today's video is basically following your Verilog on its journey from text on a screen to hardware on silicon. Let's quickly bring back the big picture from our previous video. We start the specification. What should the system do? Then comes architecture. How are we going to organize the solution? Then we reach RTL and Verilog. After that, we verify the design, synthesize it, obtain a gate level representation, move through physical design, and finally reach fabrication and the chip. Today, instead of memorizing this as a list, we are going to understand what each stage actually means and why Verilog sits where it does. So, as you can see in this particular VLSI design flow, first we have design intent of specification, what should it do, architecture, how we built it. Then RTL Verilog, our focus. RTL Verilog is used for the hardware description. Describe the digital hardware using Verilog HDL at RTL register transfer level. Next, implementation flow. First is verification. Does it work? Synthesize. RTL to hardware. Gate level netlist. Gates plus connection. Physical design. Place plus route. Fabrication design to silicon, the chip, the final product. This is the final product, what we are in the hand. Verilog doesn't become a chip directly, it goes through this complete flow. So first is specification. Before nobody or anybody writes Verilog, somebody has to decide what the hardware is supposed to do. Suppose the requirement is design a 4-bit synchronized counter with reset. We are asking what the hardware must accomplish. That sentence is specification. It tells us the hardware functionality. It does not tell us the Verilog syntax. It does not tell us the exact gates. It tells us what is required. So remember, specification answer the question, what should the hardware do? The next is architecture. Now we know what the system must do. The next question is, how are we going to organize the hardware to do it? For our counter, we need storage, incrementing logic, and control. So conceptually, we can think of a clocked register connected with increment logic and reset control. Architecture is therefore the bridge between the requirement and the detailed hardware description. The specification says what architecture starts explaining how. And now we finally reach Verilog. Verilog lets us describe the intended digital hardware. At the RTL level, we can describe register, combinational logic, and data movement and clock behavior. This is important. Verilog is not the chip. Verilog is the language we use to describe the hardware that tools will later process. So, when you write Verilog, you are not writing a normal software program that simply runs line by line. You are describing a hardware system. Let's keep one example with us throughout the video. Our 4-bit counter. The requirement is simple. On a clock edge, the counter increments. It reset is active. It goes back to 0. Reset forces the count back to 0. Now, if we have a specification and architectural idea, we can express that intended hardware using Verilog RTL. The interesting part is what happens to this description after we write it. Here is a compact RTL code. You can see always at the rate post such clock if reset count should be less than equals to 4 tick B 0000 else count should be less than equals to count plus 1 tick B1. The post edge tells us that the state changes with the positive edge of the clock. If reset is active, count becomes 0, otherwise count gets incremented. Don't worry about memorizing every syntax right now. Our question is bigger. What hardware does this description represent? And where does it go next? Now translate the code into hardware thinking. The count value represents stored digital state. The positive edge tells us what the state updates. When the state updates. The addition by 1 implies incrementing logic. So instead of seeing only lines of code, picture hardware, increment logic feeding a resistor with a clock and reset controlling the resistor. This is the mindset I want you to develop throughout this course. Whenever you see Verilog, ask yourself, what hardware is this describing? Next step is verification. Step 4. Okay, we have RTL. Can we immediately send it for manufacturing? No way. First, we need to check whether the design actually behaves as intended. There is where simulation and verification come in. For our counter, we might expect reset to produce 0000, then clock 0001, then clock 0010, and so on. If the result is wrong, we go back to RTL, fix the problem, and simulate again. This distinction is extremely important. Simulation checks the behavior of the design model. Does my design model behave correctly under the test I give it? Simulation does not manufacture or physically implement the circuit. It does not place gates on a silicon wafer. So don't say my simulation passed, therefore my chip exists. A simulation is a verification step in the journey. Always keep simulation and physical hardware separate. Now we reach one of the most important transitions, synthesize. Synthesize takes synthesizable RTL and determines a hardware implementation representation that can realize the described behavior. For our counter, the RTL implies storage element, increment logic, and control logic. The synthesize tool works toward an actual hardware structure that implements that intent. This is the moment where we move from RTL design toward implementation. What comes out of synthesis? A major output is a gate level netlist. Think of a netlist as a description of a hardware elements and their connection between them. RTL is more abstract. A gate level netlist is more implementation oriented. So the journey looks like RTL synthesis gate level netlist. The design is becoming progressively more accurate, concrete. You can see this is the one of the simplest diagram to remember. You start with RTL or Verilog. The synthesized tool processes it. The result is the gate level netlist. Notice what this tells you. Verilog is not the final representation. It is the one of the important description level used before the design move toward lower level implementation. Now let's zoom out again. Above RTL we have specification and architecture. These stages are concerned with system intent and low level implementation. At RTL, we describe the digital hardware in a practical design abstraction. Below RTL, synthesize gate level logic and physical design progressively expose more implementation details. That means RTL is a critical bridge in digital VLSI design. Verilog is useful in more than one part of our thinking. First, we use it to describe intended digital hardware. Second, we can use that description as simulation to check behavior. Third, synthesizable. Verilog can be used as input to synthesize tool. But one warning, not every Verilog construct automatically represents synthesizable hardware. We will study that distinction in much more detail later. Let's make three-stage completely separate in your mind. Simulation, synthesize, fabrication. Simulation asks, does my design behave correctly? Synthesize asks, what hardware implementation can realize this RTL? Fabrication asks, how do we physically manufacture the chip? Same project, completely different questions. Confusing these stages is one of the easiest ways for a beginner to misunderstand the VLSI flow. These are the different stages with different goals. Let's use another example, a 2 is to 1 max. The requirement is choose between A and B using select S. If S is 1, output is B. If S is 0, output is A. That is our specification. We know what the circuit must do. Now let's follow the same idea through Verilog simulation and synthesis. For a simple mux, we can express the logic directly with a continuous assignment. The expression says that y depends on A and B and the select signal S. The key point is not the syntax itself. The key point is that the Verilog expression is a description of a hardware relationship. That description can be simulated and synthesized. Now follow the mux through the flow. First, Verilog describes the intended logic. Simulation checks whether the output follows the expected selection behavior. Synthesize then determines a hardware implementation. Representation can be represented using gates and connections. So again we see the same pattern: description, verification, implementation. What you see here is the educational big picture. In industry, the flow becomes much more detailed. There are multiple levels of verification, constraint, timing analysis, power analysis, synthesis steps, physical design stages, checks, and sign off activities. Don't try to memorize every industrial tool or stage today. Your right now is to understand the architecture of the flow. Mistake number one. Verilog is basically C or Python. Yes, Verilog has things that look familiar. If case, operator, always block, but the purpose is different. Software describes instructions that executed by a processor. Verilog describes hardware behavior and structure. So whenever you write Verilog, train yourself to ask what physical or logical does this imply? Mistake number two. I wrote Verilog so I have the chip. No. Verilog is the only one stage in the journey. Mm, No. Think of it like a blueprint. A blueprint is extremely important, but a blueprint is not the finished building. Mistake number three. Mistake number three is my simulation passed. So everything is perfect. Simulation is extremely important, but it only checks the behavior and scenarios you test. It does not replace synthesis, timing analysis, or physical implementation checks or final sign off, not final sign off. Two, a successful simulation means you gain confidence in functionality. It does not mean every engineering question has been answered. RGPV exam viva, you must know for exam and viva be ready for 4 questions. Where is Verilog using the VLSI design flow? Differentiate between simulation, what is gate level netlist? How does Verilog directly manufacture a chip? If you can answer this clearly, you understand the core of this video. A strong Viva answer would be Verilog is primarily used to describe digital hardware, specifically RTL. The RTL can be simulated for functional verification. Synthesizable RTL can be processed by synthesized tool to obtain a hardware implementation representation. That representation continues through physical design and eventually fabrication. Notice how this answer explains Verilog's position, not just its definition. Now connect this to real career. An RTL designer works close to Verilog RTL. Stage, they reason about register, combination, logic, clocks, and synthesizability, reset behavior. They also work with verification and downstream implementation team. This is why learning Verilog as just syntax is not enough. You need to understand the hardware and the flow around the RTL. Let's pause here and put the whole lesson into one idea. Verilog is not the destination. It is a description used inside the journey from design intent toward hardware. RTL connects what the designer wants the system to do with a lower level implementation that can eventually become silicon. The same design becomes more concrete as it moves through the flow. If you remember this one diagram, specification, architecture, RTL, verification, synthesize, gate level netlist, physical design, fabrication, chip, and where is the Verilog? Right here. That is the answer to today's question. Then, before we finish, ask yourself 5 questions. Specification, what is the required architecture? How will you organize the solution? RTL, How do we describe the digital hardware simulation? Does the description behave correctly? Synthesize what hardware implementation can realize the description. Now you know exactly where Verilog fits in the VSI design flow. But that's create our next question. If Verilog can describe hardware, and are there different ways to describe the same hardware? Absolutely. We are about to explore different Verilog modeling styles, and this is where things get really interesting because the same hardware can be expressed from different viewpoints. So, in the next video, we'll move from where Verilog fits to how we use Verilog to model hardware. You are building skills for RTL Design Engineer, Verification Engineer, Physical Design Engineer, VLSI Architect. The journey has just begun. This is our just introduction of Unit 1, ED302, Introduction to HDL. We have covered lots of foundation videos and now we are building our syllabus videos. So, see you in the next video. How many different ways can we describe the same hardware? If you like this video, give the thumbs up, share this video with your friends, and do subscribe for the further VLSI introduction to HDL journey. Thanks for watching.